Good, then I'll start something totally new, which is as exciting. So let me do this here. This is Turing models or Turing patterns. So now we totally step out of this idea that we want to have thermodynamic considerations. We'll take a very mathematical perspective, and that's basically the one Alan Turing did in his quite famous paper in 1952. What Turing asked in his paper is basically the following. Say you have two fields, let's call them A and B. So you have two species that you call A and B. And you want to know the time evolution of A and B. And all you say is you combine two very elementary objects, namely reaction and diffusion. The functions that characterize the reactions I denote here by f and g. They're completely arbitrary. They can be any linear or nonlinear or whatever function as dependent on A and B. Those are reactions. And you know all about these reactions. We have studied those two-component reaction dynamics early on in the lecture. Right? There's this complete classification scheme of two-component reaction dynamics in terms of the eigenvalues, which you can determine by the trace and determinant. You know, this picture of getting spirals, all kinds of different attractors in 2 dimensions. And you know that this will lead to fixed points. And the most general thing you can get is maybe a limit cycle in 2 dimensions. But say if you exclude the limit cycle, you always get some kind of stable, unstable fixed points. So Turing's idea was to say what happens as you add reactions to it, and diffusion to it, such that my species A is diffusing with a diffusion coefficient A, and the species B is diffusing with a diffusion coefficient B. And in general, let's say dA is not equal dB. And you will see later why this is important or not important when we study the system. You can also think of this as vectors, right? Doesn't really matter. Then this would be Laplacian instead of a linear term that's only depending on x. All right, if you try and analyze the system, the best way to look at that is really in terms of phase space. So you plot here A and B as your dynamic variables. And then the fixed point, I'm just making this up. So let's say this is f equal to 0. And let's say this is g equal to 0. Then you see reactions alone, they will pin you down to a fixed point like so. And assuming now this fixed point is stable. Right. That's an assumption. It doesn't have to be. It's also not the only case that you can have. You know, in 2 dimensions, you can have bistability, you can have limit cycles, and many other things more. For now, just let's say we assume that the homogeneous steady state is uniform. So we assume that the homogeneous steady state is a unique state, so no bistability occurs, no limit cycle occur, and it is stable to spatially uniform perturbations. Right? And now you say, given that something is really stable against any kind of uniform change that you make in A and B, what's the effect of diffusion? It's kind of a weird question, because diffusion intuitively does what? It makes things uniform, right? It spreads out things in space. If there's a gradient, there's fixed law. Diffusion will try to make any kind of gradient vanish in the system. And in addition, you have now the reactions, and they basically do the same thing. Namely, they give rise to a spatially uniform steady state. So you wonder, why should this be interesting? Why should there be something non-trivial coming out from combining two things that on their own have the same tendency of mixing things? So let me do the formal analysis first, and later give you the intuition. So let's do a linear stability analysis. Where I'm saying that I look at deviations of my concentrations from the fixed point A star, B star. So from this fixed point, A star, B star. And as I do so, let me write the equation of motion for those deviations. And that will then be the Jacobian delta U. That's the one you get when you just do a homogeneous system with any kind, with no spatial gradients. And you add to that plus diffusion d times nabla squared of u. And this d here is a diagonal matrix containing the two diffusion coefficients dA, dB. I could also make it more general and say there's cross diffusion between the two different species A and B, and then this would become a full matrix. And J is the Jacobian, and that's, as you know from our previous analysis, that is DAF, DBF, DAG, DBG, all evaluated at the fixed point. Okay, so that's what you get in terms of the linear stability analysis. And now from the assumption that we make, so the assumption is that our fixed point A star B star is stable to homogeneous perturbation. So if we look at the trace of the Jacobian, which is the sum of the eigenvalues. And when we look at the determinant of the Jacobian, that's the product of the eigenvalues. This is Fa plus Gb. Reading this off, so I'm denoting this as Fa, etc. So the index of F is indicating the derivative. Stability means, just look at your stability diagram of two-component systems. That's the sum of the eigenvalues is negative. Right? So then both can be negative. But you also need that the determinant is positive. And then you're sure that both eigenvalues are actually such that the system is stable. Fa Gb minus Ga Fb. Okay, that's what we assume. That's just what I drew here in pictures. Our homogeneous steady state is stable to local perturbations. And then we say we do a Fourier analysis as before in the spatial domain. And as always, for simplicity, we don't take any kind of weird spatial domain. Just think of something of infinite extent. And then you know that we get at an eigenvalue problem for the eigenvalues sigma q, the eigenvectors eq. This is then a very trivial generalization. You have the Jacobian, and from taking the Fourier transform of our Laplacian, we get minus dq squared. So basically a diagonal dA q squared, and the other diagonal term dB is q squared. And that I define as my new Jacobian. That's the modified Jacobian with respect to before. And all you do is you add to the diagonal element dAq squared and the lower diagonal element dBq squared. So from that, you know the eigenvalues by solving the characteristic equation. So the determinant of JQ minus sigma q and the unit matrix has to be 0. And from that, again, we had this quite a few times in the lecture, you get a half the trace of this modified Jacobian plus or minus the square root of the trace of the modified Jacobian minus 4 times its determinant. And as usual, we have tau being the trace of this modified Jacobian and delta q being the determinant of this modified Jacobian. Yeah? Oh yeah, for sure it is. Thanks for noting this. Okay, so it's very straightforward. All you do is you generalize this to something that contains the wave vector dependence. And now we can find the stability conditions for that. So we have the trace. What's the trace? The trace is the trace of this object that we had before. So the trace of JQ is the trace of J minus Q squared trace of D. What do we know about this? We made an assumption. The assumption we made is that our steady state is stable with respect to homogeneous perturbation. That means the trace of J is negative. I'm subtracting something which is for sure negative. So this is for sure negative as well. And that means the sum of the eigenvalues has to be negative also in this general case. That means from the two eigenvalues, and let's say I'm taking plus as the one that's larger, that's my choice, I have to have that this here becomes positive, and only if the determinant delta Q is less than 0. Right? So here we had positive, that means stability for fluctuations that change the amplitude. Here we needed negative to have an instability against spatial perturbations. So now let me show you, or I draw it. So when you draw the dispersion relation, or let me just draw the delta of Q, determinant as a function of Q squared, then this will start from some delta 0 being the one for Q equal to 0. That needs to be positive by assumption here on the right-hand side. Okay, so this is by assumption positive. That means my corresponding homogeneous steady state is stable to uniform perturbations. And then you do have a structure that looks like so. Because when you evaluate delta Q, you will get a corresponding expression. So let me write it down so you see it. Delta of Q, when you write it down, is Fa minus dA Q squared times GB minus dB Q squared minus GA FB. And I want this to be less than 0 for the system to have an instability. Here I drew it to be positive, so there's no instability yet. And what needs to happen is that at some point this here touches 0, and later on this will be like so, where it goes underneath of 0. That here defines a threshold value that we call QC squared. And here on the left and on the right you have a band. And this band defines the band of unstable modes. When you're here in between, then the determinant is negative. So meaning that for that band between Q1 and Q2, you have unstable modes. We can determine a few of those quantities just that you know them. Okay, so this QC squared, hope I do this right, but let me check then later, is FA dB plus GB dA divided by 2 dA dB. And the condition for instability that you derive from doing the analysis of this function here is that you need to have FA dB plus GB dA larger than the square root of 4 times dA dB times delta 0. And this condition has a name according to the people that derived that. So Segel, the same that we already talked about in the Keller-Segel model. And this is called the Segel-Jackson condition. Okay, so there's a very clear-cut formula that defines under what conditions you'll get the instability. And that's then also called a Turing instability. The way this looks like when you plot the function sigma and not the delta. Let me draw this here. So when you draw the eigenvalue sigma q plus as a function of q, this typically looks like so. This is sigma 0 plus. And that needs to be like so because we have assumed that the spatially uniform state is stable against any uniform perturbation. So the eigenvalue at 0 wave vector has to be negative. And then when you plot it, this is the structure that you typically get. And here in between, this is again our band of unstable modes. Good, let's stop here. Do you have questions? Yeah?
Regarding the sigma q equals to 0 at q equals to 0, because I think in previous lecture we mentioned this also relates to the conservation.
There's no conservation law here, right? We are completely outside. That's what I said in the beginning. We are now completely stepping outside of conservation laws, outside of thermodynamics, outside of anything you know about the physics of the system. This is asking a fairly mathematical question in the beginning. You say you have diffusion and you have reaction. There's nothing constraining F and G. And there is nothing really special to the other terms that just have isotropic diffusion for both species. And given such a model, where I try to explain that this term has the tendency of making things even, this term has the tendency of making things even in space, uniform in space, which is found by a mathematical analysis of the homogeneous steady state, that there is a regime of parameters given by the Segel-Jackson condition, this one, that defines a parameter space where a homogeneous steady state is unstable to spatially non-uniform perturbations. And the instability has a fingerprint, which is this. It's a fingerprint where you have a band of unstable modes that's bound away from 0. Remember, in the Kahn-Hillard model, it extended to 0, so it contained long wavelength modes. Here it doesn't. There's a lower bound and an upper bound. People call this also sometimes a type 2, a type 1 type of instability. Okay? And the Cahn-Hilliard is one that's type 2. They're distinct because here you don't have long wavelength modes, in the Cahn-Hilliard model you have. So that's all we did for now. A mathematical stability analysis of a two-component model that Turing defined in his 1952 paper.
I understand, like it's because of the diffusion term we had, like forbid us from having a possible conservation law and resulting in the non-zero sigma q at q equals to 0.
Here we don't have a conservation law, but you're right, if you add a conservation law, things will change. We'll study that. Right? The absence of a conservation law has here implications. One is that you have two functions f and g. If you were to have a conservation law, you would need to add up the two, and those terms would need to cancel. They don't. And that's why the structure of our phase space for the homogeneous system is looking like so. And because we do not have this conservation law here in general, the zeroth order, the eigenvalue at q equals 0 is negative and not 0. All right, please.
What kind of conclusions can you draw regarding the formation of pattern from what we just saw?
In principle, nothing yet. So because this is a linear stability analysis that only informs you about the first growth of the modes. Now go back to Cahn-Hilliard. There we saw, again, similar type of instability. You have growth of finite wavelength mode. And then we saw there's coarsening. This coarsening shows Ostwald ripening. And in the end, we have a steady state, a thermodynamic steady state, where you have one bubble, or one liquid droplet in a sea of vapor. Here, you expect something different. So imagine that this instability is barely there. So imagine a situation where you barely have something that has an unstable mode here. Then this mode here will be the only one that grows. And because there's only a few in the neighborhood, there's not much nonlinearity that can happen. Right? There's only this one single mode that's predominant. And it turns out that you can do a analysis, a perturbation kind of theory in the vicinity of the bifurcation point to a Turing pattern that shows you it selects a pattern of a finite wavelength. And the finite wavelength is this one. Okay? And this is linked to the fact that you have this small band of unstable modes in the vicinity of the transition. In the other case, you have long wavelength modes and they mess up the analysis, right? Because you have then coupling between different kinds of modes, they're long wavelengths, and this leads to coarsening in general. Good, we discussed Turing models, Turing patterns yesterday, and this is the model, right? So we have a mathematical model for two components that have some general reaction scheme encoded by functions f and g, and both of the species diffuse at diffusion coefficients that are different. And what we learned is that the interplay between diffusion and reaction can give rise to pattern formation, which is at first sight a bit surprising. What we also did is linear stability analysis, which is very standard. So you expand the operator to linear order. That means you have the Jacobian for the reactions, and you remain with diffusion operator as is. Then the total Jacobian is the one for the reactions plus the term coming from diffusion. And then you just check the conditions on the trace and determinant for a two-component system, and you learn from that under what conditions this can become unstable. The trace here always has to be negative because we assume the system to be stable to homogeneous perturbations, and this term is negative, so this remains. That means the decisive question is whether the determinant is positive or negative. And in that case, then you have the system becoming unstable when it's negative, and you have a band of unstable modes. The condition for this band of unstable modes was given by Segal and Jackson some time ago, and it's this relation. So as we learned last time, it connects the partial derivatives of the reaction terms, F and G, with diffusion coefficients, such this is larger than the square root, again, of a term involving the diffusion coefficients, and delta 0, which is this value of determinant at wave vector equal to 0. And when you really want to plot the dispersion relation, you have to solve the standard relation with the trace and determinant, and what you find, it has this typical shape, such that as you increase the ratio between diffusion coefficient of species B and species A, at some point, like here, you get a band of unstable modes between Q1 and Q2. And this we call a Turing instability because it has a lower and an upper bound. It's bound away from 0. There's no long wavelength instability. And also the dispersion relation is fully real. There's no complex eigenvalue that we have here. It's just a real eigenvalue between Q1 and Q2. That's what we look at here specifically. All right. Now a heuristic analysis. So what we just saw was a very formal mathematical analysis where you just go through a Fourier transform and looking at eigen values. You can also argue differently. You can say, let's have the system be described by reactions and pick one of the rates that you have as the typical reaction timescale. So tau here is just encoding how long a typical reaction takes. Okay, so it's a reaction time scale. And then in addition to a time scale, you have length scales. And these length scales you can create by combining the time scale of reaction with the time scale of diffusion. So it basically says how far do you get by diffusion during a time given by this time scale tau. And these length scales are in general different for the species B and A because the B and A species have different diffusion coefficients. So that means when you wait for a time tau, the length both these species diffuse is different, so that they mix. They go different scales. Right, so let's visualize that. So here I indicate these two length scales, and I assume that the length scale for species B is larger, and that's what I mean, right? Over time, starting from some initial distribution that can be the same for both, because they have different diffusion length, they will demix over a certain time period. And this demixing you can act on by reaction. So this is just happening because of diffusion operators. There's no reactions encoded yet, other than the fact that I have here assumed a certain time scale. So let's say we have a particular scheme of reactions, and I want to visualize that by this simple network. So you have two species, as we say, and the two species I assume now to be such that A amplifies itself, so it's autocatalytic. If there's A, it produces more of itself. What it also does, by assumption, is that A is suppressing, is enhancing the B as well. So that's the plus sign here. And B is doing the opposite to A. It has a negative feedback, right? A enhances B, but as A enhances B, B is suppressing the A. And that you can say is an activator-inhibitor scheme. A is activating itself, and B is inhibiting A. So what does that mean now? So let's look here at this picture and think about this very heuristically. So here we have this demixing between A and B. Here's a lot of A. What does A do? Well, it enhances itself, so it amplifies the amplitude. It will make it grow. A is enhancing also B, but B, if there's a lot of B, it will suppress the A, it will push it down. So as you take this together, the effect is such that A activates itself, it makes the peak even sharper, and B is inhibiting the A, so it's pushing it down, confining the A to some narrow region. Okay? And that heuristically is a mechanism by which you can enhance density contrasts as given first by diffusion alone, and that's a heuristic argument to say that such a mechanism can give rise to pattern formation as it amplifies the initial contrast. And that's usually referred to as short-range activation and long-range inhibition. Short-range by A and long-range by B. That's let's say, a rule of thumb or some intuition that you can have for such a Turing two-component system. All right. Now let me do all this with slides because it's very straightforward. I can give you an example of such a Turing model. It's a made-up example, made up by Swift-Hohenberg some time ago, just to have a conceptual model that you can think of and where you can do a full analysis with all the parameters in the system. So what Swift-Hohenberg was assuming is that you have these sets of reactions. The first reaction between the two species A and B is such if B meets 2A, so it's a trimolecular reaction, then you delete the B and create the A. So you need two A's to turn the B into an A. That's a feedback mechanism, right? 2A makes more of the A. The A's are produced, production of B, and degradation of A. That's the set of set of reactions. Now you can turn this into a differential equation, just considering those reactions, and give the various reactions here certain rates. So gamma that you see here is the overall reaction rate. It measures the overall speed of the reactions, including all the ones that are listed. So it's our basic time scale. Better to say the basic inverse time scale because that's a rate. So time scale is gamma to the -1. Then mu and lambda, those are the processes where you produce A and produce B with rates, relative rates mu and lambda. Then we have this term A squared B, which I take as the basic unit of time. This is this trimolecular reaction. And minus A here denotes the degradation of A. And of course, if you have a plus term here from the trimolecular reaction that produces more A, you have to have the corresponding minus term for the reaction of species B, right? So that's the well-mixed dynamics. It's an ODE system, a two-dimensional, two-component ODE system that you can analyze by standard methods. And reaction diffusion dynamics is simply this scheme plus the two diffusion terms for species A and species B, right? Now let's first do the analysis of the two-component system. You can do this formally, and you will find this in my lecture notes. But just here, the two typical situations that you can get when you do such an analysis. There is this blue curve that you see, and there's the orange curve, this one here. They are the two null lines, f equal to 0 and g equal to 0. So they define the equilibrium points, meaning that the intersection point, this one here, will be the corresponding fixed point that you have in your system. Now this fixed point that you have when you do the analysis of the ODE can be stable. Here, when you do the analysis, you find it spirals in here in such a form to this stable fixed point. You can also have that the fixed point here is actually unstable, like so. So you see here the flow lines move out to the boundary, but from the boundary they move in. So in that case, when you do the analysis, you have a limit cycle. Meaning that as you do the ODE analysis for this two-component system, there will be a stable fixed point scenario, and there will be a scenario where you have a limit cycle. So stable spirals or unstable spirals, and in the case of an unstable spiral, you have a limit cycle. Okay, you can do this for the full parameter range. The parameter range here is encoded by mu and lambda. And let me show you now the corresponding phase diagram in a second. So let me go back here. If you do linear stability analysis, you can perform the corresponding analysis, and you find that for that condition here, lambda minus mu is lambda plus mu to the third power. There's a stability bound for this fixed point that I showed you, where it becomes unstable. And when it becomes unstable, you have a limit cycle. So this here marks the onset of a Hopf bifurcation, where you go from a stable to an unstable spiral that then transitions in the long run to a limit cycle. That's an instability of the homogeneous steady state, right? I don't really account for spatial gradients here. There's no diffusion entering this argument. That's just the ODE that we have. And remember, for a Turing system, what we wanted to analyze is the regime where you do not have a Hopf bifurcation. By construction, right, we assumed in the analysis that I gave you yesterday that the fixed point of the ODE system that we start with is a stable fixed point. And we asked, what is the instability or stability of that fixed point against spatial perturbations? Here we see we have actually two regimes. We have a regime for which we can ask this question about Turing stability, and another regime where the homogeneous steady state is already unstable to a Hopf bifurcation and shows a limit cycle. So we can also do the linear stability analysis, and that's again very, very straightforward. As you saw, we have the general formula. It's the Siegel-Jackson condition. And the Siegel-Jackson condition, if you write it out for the Schnackenberg model, it translates to this formula, where the D that we have here is the ratio of diffusion coefficients for species B relative to species A. And again, this is some kind of line in the mu lambda phase space. This is also a line in mu lambda phase space, just written in an implicit form because these are third order polynomials. So let's plot these lines in phase space, and here they are. So horizontally I have mu, and vertically I have lambda, the two rates characterizing our reaction scheme. And then I indicated in the colors matching with the colors for the stability analysis, the blue and the orange line. The blue line is just giving you the Hopf bifurcation line. So as you are outside here and move in here, the system starts to oscillate. But on top of that, you also have an instability line in orange that marks an instability to spatially inhomogeneous perturbations, right? So if you're here, and if you're very close to this point here, then you might realize that there's the blue curve that comes first, and then comes the orange curve. So here, as you move up, you would go into a system where it starts oscillating, but there would be no spatial perturbations, because they're still stable to spatial perturbations. And then, after the oscillations, you have another instability where now our system breaks up in terms of spatial organized structures, because there's also a linear instability to spatial perturbations. If you walk along this line, there is no Hopf instability. There's no Hopf bifurcation. So here, if you move along this line, you just have a standard Turing type of instability as we had it yesterday in the lecture. Here, the corresponding homogeneous steady state is stable to spatially uniform perturbations. There's no oscillations, so you only have this band of unstable modes that drives a Turing instability. Hope that's clear. It's just an example of how things work out. And the analysis that we performed yesterday is only for transitions in this direction, not for transitions where you go over a Hopf bifurcation. All right, now let's see what you get. These are now numerical simulations. These numerical simulations are done in different regimes. So you take the Schnarkenberg model, put in the parameters, mu equal 0.1, lambda 0.9, and note here, the diffusion coefficients are very different. You have 1 for A, and you have 40 for B. And that's typical. So if you want to have a phase diagram like so, where you have these Turing instabilities, you typically need to tune the diffusion coefficient of one species to be quite an amount larger than the other one. Typically something like 5 times as large. Otherwise, you wouldn't get such a Turing type of instability. And we put ourselves here at this spot, right, in our ODE, or our linear stability phase diagram. And this is what you get. So initially, I can do this slower. Right, if I grab here this, then you'll see we start from some random initial condition. Then you have some initial pattern forming. And now, as I let it go, you do have the formation of patterns. And they're pretty much, and that's something you should notice, have the same length scale as you started out with. So that's very different from what we learned in the Kahn-Hilliard model, where you initially have these patterns, but then they coarsen over time, and these droplets become larger and larger and larger. Here they don't. Here they stay at a finite size. Okay. Good, let's go to a different regime. Let's now go there, where you have 2 types of instabilities. The system is unstable already to spatially uniform perturbations and thus oscillate. And it's also unstable to spatial modulations. And that's then reflected in this type of behavior. So this is the dynamics. Initially, you get blinking, so oscillations. And it continues to blink. And then you also have the spatial perturbations kicking in that you had in the initial data. And then you see that in the long run, you also get a structure that has quite a well-defined length scale in terms of the size and the distance between the domains that you see here in red. All right. So are there questions concerning that? This is basically what I wanted to say about the Turing model, the 2-component version of it.
So inside the Hopf application region, why aren't we seeing the mini cycle?
Why don't you saw it, right? The blinking was the initial one. Then later on, that's the question we addressed today. Once you go away from the linear instability regime, you need to worry about the interaction between the different modes. And note that the Hopf bifurcation modes, they are happening at wave vector equal to 0 because they already exist in the limit of a homogeneous perturbation. The Turing band is bound away from 0. So you have a mixing of modes, which are long wavelength oscillations, right, that you saw in the background, and more shorter wavelength spatial instabilities. And then as modes grow and become large in amplitude, you can no longer think of those modes as independent entities. They start interacting by the nonlinear terms that you have in the equations. And then, the linear stability analysis cannot really tell you what the outcome is. What I want to do, yeah? Good. All right, now let us go to an equation which is a version of this, but in a form that makes a few things more explicit. So this equation that we study is named after Swift and Hohenberg. And it's basically trying the following. So remember, for the Turing system, if we have the dispersion relation as a function of Q, the basic feature of such a Turing instability is that you have this band of unstable modes where there's one mode, QC, that grows the fastest. So with the Swift-Hohenberg equation, we take this kind of dispersion relation, build it into the equation, and then study what kind of properties a simple form of an equation that encodes such a dispersion relation can have. So let's try and write this down. So let's say we have dt phi of x and t. Phi is a field. And I take a term which grows. So mu is kind of a growth rate. And then I do what I just said. I take the dispersion relation and basically build it into the model. So when you do Fourier transform here, this is minus q squared plus qc squared. So you see this term here basically just encodes a dispersion relation like so. And then I add a simple nonlinearity. And it's basically constructed in a similar fashion as you construct model A or model B, all these classical models that we studied. So you just write down the simplest form you can imagine that is a scalar field theory and contains some nonlinear terms. There is more complicated versions of that. So you can also say that you replace this here by some general nonlinear function of phi. For example, you could take n of phi being something that also contains a term phi squared and a term phi to the third. But anything else is allowed. I just wanted to, study equations of that type. Invented by Swift and Hohenberg to be minimal models of certain physical phenomena. And one of those phenomena, which you might know, is Rayleigh-Benard convection. So it's a fluid with a hot and a cold surface. And because you have a hot and a cold surface, you get convection rolls like so. And this model here is a baby version, a minimal version of a more complicated hydrodynamics model for Rayleigh-Benard convection. That's one motivation. Another one is some more recent work done by the group of Jörn Dunkel at MIT. It's already 10 years ago, where they were interested in wrinkling patterns of spheres. And here they applied the Swift-Hohenberg model to study the interaction of patterns with the morphology of spherical shells. And then they analyzed mathematically typical types of wrinkling patterns on such an elastic manifold. What we want to do now is to analyze this equation that you see mathematically. And the first thing, which I already kind of preempted by using the scheme here, is to do linear stability analysis. So go to Fourier space. And then it's quite clear what you get, right? You get mu minus q squared minus qc squared as the dispersion relation, the square of that. And that dispersion relation has a structure which I already drew in its essence, but let me give you the whole thing. It will look like so basically. This is sigma, and this here is q. And here roughly is qc. Okay. And as you would change parameters, right, so there's a transition point where mu is equal to 0. Right, at mu equal to 0, this will have a 0 at q equal qc. Then there's also range of parameters where the mu is actually greater than, smaller than 0. Then you have no band of unstable modes. And you do have a band of unstable modes, in this case, where our parameter mu is positive. Now let us look a bit into the scales that we have here. We do have this band, right? This band of unstable modes between Q1 and Q2. And let's say that we take this as a width parameter that we call epsilon. So for us, it's a bookkeeping parameter. And we want to analyze the system for different values of epsilon. It's a bookkeeping parameter that tells us how far we are from the critical point. So imagine changing mu from positive to 0. You see that this epsilon shrinks to 0, and here it is 0 right at mu equal to 0. Okay. The mu that you have here is not of order epsilon. It's of order epsilon squared because you have a parabola here, right? And so the mu that you change here turns into something that's of order epsilon squared. So naturally, you would then use a parameter where you say that our mu is epsilon squared times mu twiddle, which is now of order 1. So that's for me to bookkeep how far you are from the critical point. The delta Q, so this here, that's of order epsilon. That's what we need later. Okay? Good. Now, how would we analyze the dynamics close to mu equal to 0? So what do we get there? How would we analyze this in terms of equations? Well, let me first do a very simple heuristic analysis. When you look at dispersion relation, then there will be, if you're a little further up, a dominant mode right at QC. So our stationary distribution, you might guess, has a contribution e to the I QCx, where I choose my pattern to be a plane wave pattern along the x direction. Okay? Could also be along the y direction or something more complicated, but let's assume we have this periodic pattern along the x direction with a wavelength given by wave vector given by QC. If you make this a little further up, there will be other modes that contribute. And let's just say I ignore that and I assume this to be the solution of my Swift-Hohenberg equation. This cannot be quite the solution because that's a complex amplitude. And this is an equation for something that's a real variable. So the actual solution that I should write down is just the solution plus its complex conjugates. So as you add it up, you get something real. Now take that and insert it into the Swift-Hohenberg equation. The left-hand side is 0 because I'm assuming a stationary state. Then I have a linear term here. This will give a linear term here as well. Then you have these gradient terms here with the nabla squared acting on QC squared, QC, that will make the QC cancel. But then you have this term which is of third order. So as you do that, you get a very simple equation. You get 0 equals mu A minus absolute value of A squared A. That equation, when you study it close to the bifurcation point, so close, well, you can directly solve it. So if you look at it, it will give you that A scales like the square root of mu. So it scales in my analysis as this parameter epsilon. That's great because it means when we are close to the bifurcation point, there's a small parameter here, namely the width of the band. The width of the band is epsilon. It will be scaling, the distance here scales like epsilon squared, such that the width is epsilon, and then the amplitude you get is also small, it's of order epsilon. And that hints towards being able to do perturbation theory, because now you have a small parameter. And that's what we want to do. We want to do a perturbation theory close to the bifurcation point. This is also called a weakly nonlinear analysis. And let me show you what the idea now is behind that. the idea is this. So the naive ansatz that I made assumed that A is a constant. That's what I did here. And then I got out the order of magnitude of the amplitude. And now I'm saying if I really want to get all the nonlinear contribution close to the bifurcation point, e to the I QCx cannot be the full solution. There must be something else to it. And these are all put into the prefactor, into the amplitude A of x, y, and t. And I call this the envelope function, while I call the I to the e to the I QCx the carrier wave. The way you should imagine this is the carrier wave oscillating up and down quite fast. And the carrier wave is something that is varying smoothly. Here you see again the scales. So the wave vector QC that determines the instability in 2 dimensions is a ring. All these are the critical wave vectors. And now as you are a little bit above the bifurcation point, there's this gray band of unstable modes. And remember the scaling. I'm assuming that the bifurcation parameter is my bookkeeping parameter that scales like epsilon squared. Then you must have that this band of unstable modes, as we analyzed here, in the x direction scales like epsilon, and in the y direction it's broader, so it scales like the square root of epsilon. Let's write this down. So we make an ansatz such that close to the bifurcation point, the solution, this is now for a 2D system, is a carrier, a envelope function, an amplitude function, times a carrier wave, and the other term is just the complex conjugate of it to make the whole expression real. That's our envelope or amplitude. And this is our carrier wave. Now let's look at the dispersion relation, sigma of q. Sigma of q is mu, or if I write it out, epsilon squared mu twiddle. And I do that, let me emphasize again, to do bookkeeping about my distance from the critical point, and do bookkeeping how the various terms scale with the distance from the critical point. This is my reference. I want it such that epsilon squared is scaling the parameter mu. And then when you do the expansion here, so I'll take the q as qc plus delta qx delta qy. Okay. So I'm starting from a carrier wave in x direction. And as you see from this plot, there's a small band. This is the delta qx that are in this small band. And in the y direction, this is delta qy. So as you insert that into the dispersion relation, you get minus delta qy squared plus delta qx squared plus 2qc delta qx. from this graphical representation, we learn that the delta Qx in terms of my bookkeeping parameter scales as epsilon, and delta Qy scales like the square root of epsilon. And when you take this in now, this information that you have from the graph, into this expression, you can just do the math. Sorry, there's a square missing here. If you take the delta Qy proportional to square root of epsilon, this is epsilon squared. So that term scales like this one. Here, this is delta Qx, but the dominant term is this one. Qc is of order 1. Delta Qx is of order epsilon. When you square it, it's of order epsilon squared. So all the terms that you have here are to leading order of order epsilon squared. And now I have all the physics in the dispersion relation on equal footing, and I can do a perturbation theory such that I carry along the structure that I have here by bookkeeping and keep all the features that are relevant for the physics close to the bifurcation point. That's the idea. And this then amounts to a multiple scale analysis. Right, and let me emphasize again, we have multiple scales here because we have this fast carrier wave of order 1, and then there's the slow variation of the envelope wave because you have just a small sliver of modes available from which you can build the interacting modes in the band of unstable modes. So what we will do is we will introduce a set of variables. We'll have the variables that are the original fast variables for the carrier wave. I call t twiddled equal t, and the same for x and y. They are for the carrier wave. And for the envelope, I want slow variables that are constructed such that I'm reflecting the features of the dispersion relation. So you see in a dispersion relation, sigma is a growth rate. That means the corresponding time I have in this slow space has to be rescaled by epsilon squared. That means I'm defining a slow time scale as epsilon squared times t. For the variables x and y, I do the same logic. Because delta Qx is scaling as epsilon, I'll introduce a slow scale, length scale, in the x direction, which is epsilon times lowercase of x. And I introduce a small scale, a slow variable in the y direction that I define as the square root of epsilon times my original variables. Such that now, when I rewrite phi of x, y, and t, I do write it as an amplitude depending on my slow variables, x, y, and t, times a carrier wave which depend on the fast variables. And here I can either write it as x twiddle or x, but I remain here with x and y because in the end they are the same here for our choice of scales. And of course, I shouldn't forget that this is the complex conjugate that I have to add for this to be real. So now we want to keep that structure and treat x, y, and t and lowercase t, x, and y as an independent set of variables. Or maybe I should take a break now. Yeah, let's stop here because that's the setup. And then from this setup, we will do the analysis after the break. But you can, of course, now ask questions if you like. So you get the setup right. Did you get the idea? No? Okay. So, again, close to the bifurcation point, there is one dominant mode, QC, and there's this gray band of other modes. The dominant mode I put here as the carrier wave, and I make a choice. I say this is in the x direction, so I actually pick this particular point. When you a little bit above the critical point, this is not the only wave vector that there will be there. So if you want to capture the nonlinear effects, you have to account for the other modes as well. So far, so good? Point is that the deviation of these modes from QC is small because you're in the vicinity of the bifurcation point. So they are small, they are of the order epsilon, epsilon square root. If I scale my bifurcation parameter mu with epsilon squared. And then that means that the deviation from QC is a small variable. It's just going to 0 as I tune epsilon to 0. That means I will get a separation of scales. QC remains of order 1, but this deviation will become smaller and smaller and smaller, and that means the wavelengths that I'm adding, they become longer and longer and longer. And I want to keep in the analysis not just the dominant wave, but also those modulations. So I need to make bookkeeping between all the different terms that I want to have in the system, and they should be kept in a consistent way away from the critical point. And for that, I introduced this bookkeeping parameter epsilon, such that I have this slow variation coming from the modes in the band, and the fast variation coming from the mode that is the fastest growing mode. And then as I insert that into the Swift-Hohenberg equation, I will need to do a perturbation theory that keeps all these terms to a consistent order in epsilon. Okay? You'll see. Maybe it becomes clearer when I work out the mathematical details.